is the evolution of fiber optics, the types, the configuration, the different characteristics, and its different variations, which we had seen in unit number 1. In unit 2, we had seen the attenuating characteristics, in the sense the scattering, the fiber loss, distortion, and many more of unit number. So of optical fiber in unit 3 we had seen optical sources, the single mode fibers, light emitting laser diodes, their types, their characteristics, and how they are being generated of which we had seen in number 3. Different types and its characteristics, the derivative equations, and so on. Then we had seen avalanche photodiodes, which are used at receivers, or pin photodiodes or pin photodetector, which are used at receiver to convert these light signals back into electrical signals, because all the information that we transmit are in the form of electromagnetic wave. So that form of wave is being converted to optics and is being sent. At receiver, it should be done in reverse of that. So that is what we had seen through avalanche photodiodes and pin photodiodes. So next, we are going to see the optical receivers. So the fundamental block diagram of optical receiver is shown here. So we have an fiber which is present in the receiver segment, where the receiver segment is coupled with the help of a coupler. Now, there is in this PD, which is your photodiode, is falling on the diode. So that is being monitored by an input power monitor. So then this here, then we have an quantizer. This quantizer this quantizer will do quantization based upon the sampling theorem. Then it is given to the filter. An amplifier or limiter is present to detect the signals. Then depending on the decision given by the clock, it is being detected and is given to a buffer. And if anything is above the signal, it is being made as a signal being lost. This is, this is your receiver functional block diagram. Next is the receiver types. There are three different types of receivers available. One is the low impedance receiver, high impedance receiver, then the trans impedance receiver. So the low impedance receiver is this circuit. We have an amplifier, we have an resistive load, we have a biasing circuit. So here, this amplifier is your integrator or a differential amplifier. So the low resist sensitivity is made easily and it is a wide band. Whereas the high impedance will have sensitivity, low equalizer should be placed. The trans range for high sensitivity has low dynamic range. It has problems. Of bitter rate. So the quality factor lies around 10 power minus 9. This is the probability of error. approximately 1 calculator of 10 power minus 9. So the receiver will have some noises because this receiver is present after the channel. So the channel will obviously add noises. So these noises can be categorized as noise, circuit noise, photoelectron noise, gain noise. And so on. So the photoelectric diagram without a showing the left side, the right hand side is shown. So also called the short quantum statistics. Photo of photodetection process leads to noise. Where the gain noise, example, gain process in avalanche photodiodes or LBM doped fiber amplifiers is noisy, EDFA. So a receiver circuit noise is that it will have a resistor and a transistor in the electrical amplifier contributing to circuit noise. Next, of noise, the noise is the where DRM is equal to square root of 4 AERB. For short noise, Gaussian noise due to the noise is the whole power 1 by 2 first root of it. So this is equal to the local noise in terms of thermal and we model let's say in parallel with the noise current source where the variance of the noise current is SI square is equal to TP divided by R. The T is the temperature, influence V is And then next is the photo detection noise. The electric current the electric current in a photo detector circuit is composed of a superposition of electrical pulses associated with each photoelectron. The variation of this current is called as the short noise. So in the diagram you can see that the photons are present with these pulses amplitudes, and the photoelectrons will move in this pulses and amplitude. The current pulses will be going in this. The current pulses. So this would be your electric current, which is your short noise. I of t with respect to t. The variations of this current is called as the short noise. You can see this is present in the photodetector. So this noise is present in the avalanche photodiodes. So these are the photoelectrons. The randomly multiplied photoelectrons will have gains in this. So if the photoelectrons are multiplied by a gain mechanism, then variations in the gain mechanism gives rise to an additional variation in the current pulses. So this variation provides an additional source of noise, gain noise. The circuit noise in the receiver can be replaced with a single random current source with root mean square value of sigma tau. So which is this. A noisy circuit and a noiseless circuit. Then next we can find the signal to noise ratio, which is the function of the average number of photoelectrons per receiver resolution time for a photodiode receiver at two different values of the noise in the circuit value. So the signal to noise ratio as a function of the average number of photoelectrons per receiver resolution for a photodiode and the avalanche photodiode receiver with mean gain V is equal to 100 is given at the bottom, where the excess noise factor is F is equal to 2, and at low photon fluxes the avalanche photodiode has a better signal to noise ratio, and the high fluxes the photodiode receiver has a lower noise. So depending upon the application you can choose it. The dependence of a signal to noise ratio avalanche photodiode gain is parameterized by the factor K, which is the ionization ratio between holes and electrons. So this is your DTS, digital transmission system. We have the electrical pulses or input pulses which are given to the LED or a laser transmitter. So this LED or laser converts the electrical pulses to optical pulses. So we get optical power pulses like this, and this is being given to an optical fiber cable depending upon the application. So then they are being sent. Coordination and disordered optical power pulses goes like this. So then this signal, which is attenuated and optically distorted power pulses are being given to the pin photodiode or the avalanche photodiode, so where the optical signals that are being received are being converted back to electrical pulses, electrical current pulses containing photodetector noise. So this will have some noise. So this noise is being amplified and filtered. Then voltage pulses and amplified noise is present. Then we have a decision circuit with the pulse generator, where decision depending upon the complication of the signal is present is being done. Then signal processing equipment will be there that will process the electric signal, and it will be given to the corresponding receiver. So this is the design of an optical receiver, which is much more complicated than of the optical transmitter, because because the receiver will first receive a weak signal which is of distorted, and then decision on what type of data it is, whether it is a noise signal or a noiseless signal or a data signal, is to be classified, and it is done at the receiver. Next is the error sources in digital transmission system. So we have the photon stream h nu, which falls on the photodetector having gain m. Then it is given to an amplifier. So in each stage, what is present, we are going to see. In each and every stage, in the photon stage, we have the photon detection quantum noise, which is uh, Poisson fluctuation. At the photodetector gain M, we have the bulk dark current, surface leakage current, statistical gain fluctuation for Avalanche photodiodes. At the bias resistor, we have the thermal noise. The amplifier, we have the amplifier noise. We would have studied about the intersymbol interference in digital communication. And the same we get at the received signal in optical fibers. The same would have performed in the last experiment in optical communication laboratory. I think experiment number 4. So the pulse spreading in an optical signal after traversing along the optical fiber leads to intersymbol interference. So there are some fraction of energy remaining in the appropriate time slot that is designated by the value gamma, and so the rest is the fraction of the energy that has spread into the adjacent time slots. The receiver configuration again. Here is a h nu falling in the photodetector. The photodetector will convert the light signals depending upon the variation into electrical signals. Then it is given to amplifier and its input parameters. Then to an equalizer. The binary digital pulse strain incident on the photodetector can be written in the following form. P of t is equal to summation n is equal to minus infinity to plus infinity bn hp of t minus ntv. TB is the bit period, bn is the amplitude parameter of the nth message digit, and the hp of t is the received pulse shape which is positive for all t. Bit error rate. So bit error rate is the probability of errors that is being manipulated. The probability that the output voltage is less than the threshold when a binary digit 1 is sent, plus the probability that the output of voltage is more than the threshold when binary 0 has been sent. So it can be calculated as the number of error over a certain time interval t divided by the total number of pulses transmitted during that t, so which is Ne by Nt, which we can write it as Ne by Bt, which is B is equal to 1 by Tb. So these are the probability distribution for the received logical 0 and 1 signal pulses. The different widths of the two distributions are caused by various signal distortion effects. So P of P1 of E is equal to minus infinity to V Py of 1 Dy, which is the probability that the equalizer output voltage is less than V if 1 is transmitted. So P naught of V is equal to integral of V to infinity P of Y at 0 is at 0, then the probability that the equalizer output voltage exists V. This is the probability of error manipulation. Q of E is equal to Q1 P1 of VTH plus Q0 P0 of VTH, where Q1 minus infinity to VTH P y of 1 dy plus Q0 VTH to infinity P of y of 1 dy, where Q1 and Q0 are the probabilities that the transient present 0 and 1 respectively. This is the Gaussian distribution function. This is the bit error rate function which we have seen. Quantum limit we have discussed already in unit 2. Then signal through the optical path, just now we had seen, same diagram. Next, the fundamental operation of a receiver. So till now, if you have any doubts, you can type in chat box. Since I couldn't find any queries in the chat box, I'll proceed on to the next slide, which is fundamental operation of the receiver. The photo detector will be present. So this photo detector, which is being coupled into the receiver segment, will bring in optical signals of H nu. So the first element which is present is your avalanche photodiode or an pin photodiode that produces an electric current proportional to the received power level. Since this electric current typically is very weak, the front-end amplifier boosts it to a level that can be used by the following electronics, which is the uh, amplifier. Then the signal is passed through a low-pass filter to reduce the noise that is outside the signal bandwidth. So then the filter also reshapes or equalizes the pulse that have been distorted as they travel through the fiber. So together, a clock, which is a recovery circuit, will take a decision such that whether 0 is received or 1 is received at V out. So the same structure, manipulation of the bandwidth at the front end, noises in the receiver. Noises are termed as unwanted components of electrical signal that tend to disturb the transmission and processing of the signal. So the random arrival rate of signal photons produce quantum noise. The dark currents comes from the thermally generated electron-hole pairs in the p layer and n layer junctions. Additionally, short noise arises from the statistical nature of the avalanche photodiode process. Since thermal noises arises from the random motion of electrons in the detector, it detects the load resistor and in the amplifier electronics. So probability of bit error. The bit error rate is the ratio of enormous bits to corrected bits. A simple way to measure the error rate in a digital data stream is to divide the number of errors occurring over a certain time interval t by the number of pulses transmitted during its interval. So this is called bit error rate. The diffusion threshold voltage, which we had seen, derived DER expression, which we had seen, probability of error calculation, just now we had seen, and as a function of signal to noise ratio. This is the receiver sensitivity. P sensitivity is equal to 1 by responsivity into Q by M, Q MF of M BQ divided by 2 plus sigma tau. So the receiver sensitivity as a function of bitrate will change for a given photodiode depending on values of parameters such as wavelength, avalanche photodiode, gain and noise. Quantum limit is that the minimum received optical power required for a specific bit error rate performance in a digital system. So this power level which we require as a minimum is called the quantum limit. Since all the system parameters are assumed ideal and the performance is limited by only the detection statistics. So this is your eye pattern or eye diagram that is obtained in optical receiver. So eye pattern measurements are made in the time domain and immediately shows the effects of wave distortion on the display screen of standard BER test equipment. The eye opening width defines the time interval over which signals this width, over which signals can be sampled without interference from adjacent pulses. The best sampling time is at a height of the largest eye opening. The eye opening height shows the noise margin or immunity to noise. The rate at which the eye closes gives the sensitivity to timing errors. The rise time is the interval between the 10 and 90% rising edge points. You can see in the diagram. This is as similar to your eye opening in digital communication that you are studying. Next is the stressed eye tests or eye pattern. So the IEEE 802.3 AE specification tests for 10 gigabit Ethernet devices that describes the performance measures using a decoded signal. This stressed eye test examines the worst case condition of a 4 extension ratio pulses with multiple stresses, where intersymbol interference or the vertical eye closure The sinusoidal interference as shown in the diagram is being done. The stressed eye test assumes that all the different possible signal impairments will close the eye down to a diamond-shaped area with the 0.10 and 0.25 of the full pattern height. If the eye opening is greater than this area, the receiver being tested is expected to operate properly in an actual fielded system. The inclusion of all possible signal distortion effects results in a stressed eye with only a small diamond-shaped opening. So this is that. Next is the burst mode receivers. The amplitude and phase of packets received in successive time slots from different user locations can vary widely from packet to packet. So if the fiber attenuation is 0.5 decibel per kilometer, then there is 10 decibel difference in the signal amplitudes from the closest and the farthest users. So if there are additional optical components in one of the transmission paths, then the signal levels arrive at OLT that could vary up to 20 decibel. A fast responding burst mode receiver with high sensitivity is required. So the guard time provides a sufficient delay time to prevent collisions between successive packets that may come from different optical network paths. So you can see that ONT packet 1, ONT packet 2, ONT packet 3 is having a guard time of T where up to 20 decibels can be present. So this is your guard time. So the relative received power level will vary depending upon the ONTs. So this is from closest ONT, this is for the farthest ONT, and this is an intermediate distance of ONT. So any queries in this fundamental optical receiver, you can type in chat box.